Welcome back. Let's take a look now at this mechanism in C++ for supporting inheritance. And what we'll start doing is actually providing a little bit of a definition to make things very precise. So when I'm talking about subtyping, let's say that I have two types, A and B. And both, remember, they stand in for sets of objects that meet specific requirements. I will write the following: A less than with a colon B, to state that A is a subtype of B, right? It's a way to say that A is a subtype of B. So in my example with the Venn diagram of before, I would have A be a human, B be a mammal, and then I would say that A is a subtype of B to mean that human is a subtype of mammal, right? That's how I would write it. I would write human less than colon mammal to say that human is a subtype of B. It has more requirements and therefore it is a smaller set of objects. So it's a mnemotechnic trick to remember the less than. The less than really refers to the set of objects. The set of object of human is smaller than the set of object of all mammals, right? Not every mammal is human, but every human is a mammal. That you read it in that direction, okay? So that's what I will write. And there is a very, very important rule when we make use of that. It's what we call subsumption. So whenever you have two types, where A is a subtype of B, right? Anytime you expect to see a B, you can provide an A. Why is that? Well, let's do it again, right? We have, remember, A is human, B is mammal. So when I say A is less than B, I mean that human is a subtype of mammal. So I'm saying each time you expect a B, each time you expect a mammal. So let's say that you have a function foo that expects a mammal reference, say. So foo expects a reference to a mammal. That's what you have. Now, if you have on your hands an A, you can pass, for example, you have A little a equal, and it's been initialized, then you can say foo of A. This is legal, right? Because my A here, let's make it precise, it's not any A, it was actually, let's use the type, a human. So I have a human called A, and I'm passing the human to a function that expects a mammal. But remember, every human is a mammal. A human is a mammal, so therefore nothing wrong will come out of executing the code that sits inside that function. That code is going to manipulate a mammal, and since a human is a mammal, it can only do the things that a mammal is willing to do. And since humans are mammal, they can do all the things that mammals do. So therefore this works perfectly fine. It's okay. That rule that basically say that here I'm expecting a mammal, that's what I expect, and I'm providing a human. In that case, it's okay. You can pass a human wherever a mammal is expected because human is a subtype of mammal. That's the key rule. You can do that and it works beautifully well. Right? So that's the basic mechanism. So let's take a look at C++ code that actually does that. So let's remove the parentheses here so that it's a little more readable. So let's take a look at that code now, right? So I have two classes, the class for a mammal here, and then the class for human on this side, right? Now you see how we specify inheritance. We basically say that human, colon, then there is this public, and then mammal. Now we've already covered public, private, this kind of business, so you know what the public here refers to. This public, the one we see at this place, right? This public refers to the fact that anything prior to the keyword is private to a human. So for example, if we wanted to keep track of attributes, we would actually put them above that keyword public. Everything after the keyword public is visible to the outside world. That's the meaning of that keyword. But now there is another one here. There is this public. And this one has a completely different meaning. This one basically says that the human while it inherits from mammal, I want that fact to be known. I want this piece of knowledge to be kept track of by the C++ compiler. The C++ compiler needs to know that human is a subclass of mammal, so that if we encounter a situation like this, it can do the right thing and recognize the code as legit. You could have not used the annotation. When you don't use the annotation, human inherits from mammal, but this fact is concealed. It is not revealed to the compiler. The compiler sees it and then he forgets about it, which means that this all of a sudden is no longer valid because subsumption does not apply simply because this fact was not recorded. So that's where it's critical to understand that we have both subtyping and subsumption. Subsumption uses subtyping to verify the validity of specific statements like this one, right? And here, by saying that something is public, you're exposing the subtyping relationship to the world so that subsumption can take advantage of it. If you don't put public, you're still inheriting just the code, right? It's inheritance of code. It's very pragmatic. But that subtyping is hidden by the compiler from the rest of the world, and therefore when they try to actually write something that uses subsumption, the compiler says, are you crazy? Human and mammal? Not related, because he doesn't have that fact. That's why this public is extremely useful and why you find it in tons and tons of class definitions in C++. Actually, you would almost feel like that should be the default. You want to expose that information. Now, it is not the default, so you have, the default is private actually, so whenever you actually write a class like this, it is imperative that if you wish to expose this subtyping relationship to the world, it is critical that you use the public annotation at the time of the definition of the subtype. When you say human is a subtype of mammal, you add the annotation, and adding that annotation saves you. Now you see that the code here, I have a mammal, a human, I print the mammal, I print the human, and I call foo. And you see the foo is exactly the foo I've declared here, right? This is the implementation of foo right here. Okay, so we have it here. That's the implementation of foo. And you see that that piece of code basically receives a mammal, prints it out, and this is it, right? There's nothing really special. I want it just to show a case of subsumption when we are making the calls to foo in this line. We have two calls, and one of them is receiving a mammal, nothing shocking, but the other one is receiving a human. Take away the public annotation here, and all of a sudden this code is no longer valid, and the compiler will complain very loudly if you try to write that. Great. So that's for a very important bit on the inheritance that was important to point out, is that first, very easy to do, right? It's just class, name, colon, then the superclass, and then you have to play and expose this fact or not by using the public annotation or not. Great. So that's what you need to remember. In this case, both calls are fine because we expose this fact through the public annotation. Okay, and that's the important thing. That's nice. If we run this code, and we're going to do that to wrap up this video, is that if you run it, you will see that the object identity is preserved. That's why I will be printing the pointers. You will see that when I'm coding foo, whether I'm coding foo with an actual mammal or a human, you will see that even if I'm passing a human by subsumption, since humans are mammals, the code is okay, but inside, when I print the address of the guy, because it's passed by reference, right? Remember, that's what I have here. It's passed by reference. Because of that, when I see the address, it's exactly the address I would expect. It's exactly the same printed outside foo and inside of foo. Nothing happened. Nothing nasty happened. The address didn't change because of the subsumption. Subsumption preserves the pointers, and that's really nice. So let's load up the code and actually see this in action. So let's go in here, and we're going to load actually, I hope it's in one of those files, and I don't remember where it is. So let's pick up a shell, grep human star.cpp. Oh, it's this wonderful file. So here I have a mammal, a human, and we started out doing it this way, right? We use public inheritance. And you see here that I'm just calling print. I'm a mammal, I'm a human. Foo, receiving a mammal, printing in foo message, and I'm calling print. Then in the main program, I have a mammal, a human. I'm initializing MR as a reference to a mammal, just to verify that subsumption works. I'm printing the mammal, I'm printing the human, and I'm calling foo with the mammal and foo with the human. So everything quite straightforward. So let's go to the shell and compile this one using the C++ standard 14. And as you would expect, no complaint whatsoever. So now I can actually run it. And what do I get? I get this message that says, I'm, and you see an address, a mammal. You see, by the way, that the address ends in 359D8. When he prints the human, that's a different object on the stack, right? So the address is different. He says I, you see the pointer, and it's not D8, it's D0, I'm a human. So clearly the human is at D0 and the mammal is at D8. Every human is a mammal. So when you're going to take that human and look at it as a mammal, I should see the same address. So when I'm in foo, I get message, I get the pointer D8, I'm a mammal. So I got the printout of a mammal, which is fine, right? The first line being called in the program is calling foo on the mammal. The next one is calling foo on the human. So what do I get as an output? I get in foo, you get the pointer with the address D0. Yes, it's indeed D0, but there is a surprise. He said, I'm a mammal. That is, even though subsumption works, when I invoked the method, I ended up having the method of the mammal being called, not the method of the human. Remember what's going on in this method? The print of the mammal says I'm a mammal. The print of the human says I'm a human. So the printouts are different. And here in foo, when I saw this guy, this human, when I saw him as a mammal, I was maybe expecting to get a printout saying I'm a human. I'm getting the right pointer. So the object has not changed. It's still a human, right? Masquerading as a mammal. And because he's masquerading as a mammal, the wrong method got called. Well, wrong, it's only wrong in your mind, depending on your background. If you're coming from Java, you're probably thinking, wow, that's weird. In Java, that's not what you would have. In Java, you would have, I'm a human, right? Even if you invoke the method through a mammal, you would say, I'm a human. That's a thing we call polymorphism. Right now, we're only discussing inheritance. In C++, you control polymorphism some other way. In Java, you don't have a choice. There is only one way to do it. You do everything polymorphic. Now, polymorphic everywhere carries a cost. C++ is performance conscious. So C++ gives to you, the programmer, the liberty of adopting inheritance with or without polymorphism. Here, I have not said anything special, so I get inheritance without polymorphism. Mainly, when I call print, I will get the print associated with the static type. So since I'm calling foo on a mammal, when I call the print, it's the print of the mammal that gets called. And this is related to how I've defined my mammal and my human. C++ allows you to choose. Of course, you will notice that C++ has a way to give you polymorphic method, exactly like Java does. But you have a choice. Once again, you have a responsibility as a programmer. You subclass, and then you decide, polymorphic, yes or no. If you decide no, you get this. If you decide yes, you get the behavior of Java. But this is your decision. And this is your mistake to make if you're not being careful. So remember, this is something that's quite important to consider when looking at this code in greater detail. So that's it for now. I will stop here, and we will continue next time looking at other aspects of inheritance. See you soon.